All right. Well, we'll go ahead and get started as the rest. Okay, come in. We'll just incorporate them. And so here, Josh, let me get you. Let me pray for us, and then we'll go ahead and get started. Father, thank you so much for how you guide us and love us. And Father, I thank you that in my own life I can see that, and I can see how you've blessed me and gifted me and directed me for certain things. And Father, I pray that you would continue to do that, and that you would continue to mold each and every one of us further into the image of Christ, that we might be better stewards of your love and your grace, and we might understand fully what it means to be your children. We ask this in the name of Jesus. Amen. You go, sir. So, hand back your packet. Your quiz and your exam should have a grade on it. Your homeworks and your lab probably do not. If you weren't marked down in any way, they weren't marked in any way. And so I think for the most part, some of you, miss points as far as, or for not presenting your answer in the proper number of significant figures. And then some of you didn't show any work, but just presented your answers. And so if you don't show me any work, but all you present is your answer, it becomes very difficult for me to know how I can award partial credit. And so just on future assessments, make sure that you present your work as you're doing that. And that way, if you don't get the right answer, I can more correctly and accurately assess your work on that problem. If it was something that you went about the problem completely wrong, that's one thing, but sometimes it's just you made a calculation error, and so that's something entirely different. All right, so this week we're talking about kinetic energy, and we're going to attach it back to what we've been talking about the last couple of weeks. And so before we actually introduce our new concept, I wanted to go back and reference homework 5 and see if there are any specific problems that you'd like to work through. I know I want to work through number 4, and in doing number 4, it's going to actually require us to have some material from the previous problems. So it actually might require us to do all the problems. So let's just do them all. Is that all right? All right. Yes. Okay, so what is the velocity of a rock? By the way, in this week, we were talking entirely about linear velocity. So because we're talking about linear velocity, now when it asks for velocity, you should assume linear unless it specifies otherwise. And sometimes it'll specify linear, sometimes it'll specify angular.
I saw a video online and the guy used an omega for the velocity.
So omega represents angular velocity, and then you could get angular acceleration, which is like linear acceleration, but compared to angular velocity. I just didn't use that representation for it, that variable, but in terms of concept-wise, it should have still been the same. In terms of measuring it in radians per second, how many circles are you completing every second, or portions of a circle? So, are you suggesting that as terms of as helpful for noting angular versus linear?
Yeah.
So not using the V?
Because it could be V equals V times R if you do them both as V.
Mm-hmm. And that's why when I did our equation for linear velocity, I'll write out linear velocity, and then I'll say it's equal to radians per second times the radius, And so that way you eliminate having multiple V's in the same one. But we could use omega for angular velocity. I didn't want to introduce that because that comes up with just a lot of really some more complex ideas with angular motion than what we need to do in this level. So for homework 5, when we're asking what is the velocity of a rock, we're dealing with this in linear velocity. And so what do we have? I thought that one was going to work, and it is not. So for number 1, we have angular velocity. And if you want to set that equal to omega, that's fine. So the angular velocity is, it tells us that we complete 6 full circles. Each circle is how many radians? 2 pi. Every second. Okay, so we know angular velocity. We know the radius is also given. It's 0.520 meters. And so tools, we have that linear velocity is equal to radians per second times the radius, right? And then what do we want? We want linear velocity. So linear velocity, all we have to do is clean this up, right? And so this will multiply the 6 through, multiply that by the 2 pi. So 6 times 2 times pi. And we get that linear velocity is equal to 37.699. We won't worry about rounding it to proper significant figures until we're all done. Radians per second times the radius, which is 0.520 meters. And we get that our linear velocity is equal to 0.520. And then now this gave us 6 rotations. It is a single significant figure. So if you wanted to, you could limit it to 1. I would suggest limiting it to 3 from here and assume this is exactly 6 rotations. But if you chose to limit it to just a single one, that would be fine. I would understand because we don't know if it's exactly 6 rotations. But I'm going to present my answer as 3 significant figures. Is that what you got? Did you do your homework? 37.7 meters per second? More or less? Maybe some differences because of rounding maybe this one before you went and multiplied it by the 0.520? No? Okay. Alright, so then in number 2, what do we have? Well, now we have our linear velocity. Right? Our linear velocity is equal to 37.7 meters per second. And that's all we have. I mean, we could put in some of the information it gave us in the previous problem. We know that the radius is equal to 0.520 meters. Yeah?
Sorry, about the first question. The final answer, or before the final answer, 37.699 times 0.520, I ended up getting 19.6.
Yeah, I did too. I don't know. I just rounded this one. I'm sorry. Yeah, so it's 19.6. Thank you for stopping me. Yeah, it's 19.6 when you multiply it through here. This one right here simplifies to 6 times 2 is 12, yeah, to 37.699. And then when you multiply that by the radius, you get it as 19.6. I had that on my phone, and then I rounded the one up above. So that means this is 19.6.
So if we only use one significant figure, we would put it to
20.
20?
Mm-hmm. Yep.
Okay.
That's what you did?
Yeah.
Yeah, and that's fine. Because if you want to make the case that 6 rotations is just one significant figure, that's fine. You can certainly make that argument. I'm going to keep it like this just because I want a little bit more precision. I guess I could have just said exactly 6 rotations and then we could have eliminated. Anytime you see exactly, or if you're doing a conversion, like if you're converting from kilograms to meters, you can assume that there are exactly 1,000 meters in a kilogram. Okay, so you're not going to limit it to that one significant figure that 1,000 has. Okay, that makes sense? Because it's exactly. So conversions are that way. Unless you know, like you've come up with the conversion and you know it's an approximation. So tools, we have the acceleration is equal to linear velocity squared divided by our radius. That's a tool we've had previously, we've dealt with, we've worked with, right? And what do we want? We want acceleration, right? Which is nice because our tool is exactly in that form. So we'll put our linear velocity, 19.6 meters per second, quantity squared, divided by 0.520 meters. So this squared is also going to make meters squared, second squared. One of those meters are going to cancel out. And so our final unit should be meters per second squared. Why is that good? That's how we often represent the acceleration in meters per second squared. So we have 19.6 squared divided by 0.520. Okay, and so now if we maintain three significant figures and you didn't limit it to the one, you should have an answer of 739 meters per second squared. Wait, no. Why are my, oh, why? Yes, you should, sorry. Is that what you have? 739, so if you did it as 20, instead of as 19.6, it'd be 20 squared, which is 400, divided by 0.5, and then if you maintain it as one significant figure, it should be 800. Is that what you had?
No, I think it's messed up somewhere. I ended up getting like 3,000.
I got
8? But not 800?
I got 800.
800, okay, yeah. Okay, so does this make sense? Okay, and then for number 3, and keeping in mind all of the problems build on each other. So when we're doing number 3, we can pull in some of our information from a previous problem, but number 3 gives us the mass, right? Mass is equal to 5.00 grams, right? And our acceleration is equal to 739 meters per second squared, or 800 meters per second squared if you rounded it to a single significant figure. Tools, Audrey? F equals ma. And what do we want? We want the force. And so force is equal to our mass, which is 5.00 grams, times our acceleration, which is 739 meters per second squared. And then, so what we get and now so I'm still maintaining 3 significant figures, but if your answer here is 800, you should have 1 significant figure. So this would be 3,700. I can't even actually present in 3 significant figures. I have to reduce to 2 or go to 4. I'll reduce it to 2. So 3,700 grams meters per second squared. And so we can't change this into a Newton because a Newton is kilograms meters per second squared, right? So the only way to change this into a Newton would be to go and convert this into kilograms, or to convert this into newtons, which would be a little bit more complex. But I can tell you, if you want to give another one, and then I'll just give you this so you can know it to be true. A gram meter per second squared is equal to a millinewton. And then I'll just give you that so you don't need to remember it or memorize it. But whenever you're dealing with this, you can, not worry about having to convert this into kilograms first. And you can just do grams, meters per second squared into a millinewton. It's kind of fun. Is this okay? So if you didn't round this, you should have 4,000 grams meters per second squared, or millinewtons. Do any of you know that? The millinewton? It's kind of fun. Alright, finally, number 4. The one I wanted to go through together, but we have to go through them all to get to number 4. It's my fault, right? I built the homework this way. Alright, so how fast would the rock be traveling 3 seconds after it left the sling? And so, we have our initial linear velocity. Okay, as soon as it leaves the sling, it's going to have that initial linear velocity, right? That's the whole idea of linear velocity. So the linear velocity is 700, no, what was our linear velocity? 19.6 meters per second, or 20 meters per second if you rounded it to a single significant figure. We have our acceleration, which is equal to 739 meters per second squared, or 800 meters per second squared, if you limited your answer to a single significant figure. And this is, oh, and then we know time is equal to 3.00 seconds. And then we have a tool that says acceleration is equal to linear velocity divided by time, or a change in linear velocity divided by time. Let's not introduce new symbols. Change. We'll come back to that delta because we'll use a change in linear velocity divided by time. That was a tool I gave you last time and to use to solve the last homework problem from the previous week. Right? Do you remember this tool? And then so this we want our final velocity. Right? We want to know our velocity after 3 seconds. But in order to get that, we need to know how much the velocity changes. Right? We know what the velocity was at the beginning. We want to know what it is at the end, but the only way we can attach those two is to know how much it changed. Make sense? Okay, so if we're going to solve for this, how do we get time away from here? It's currently being divided away. We multiply time to both sides. And so we get change in linear velocity is equal to our acceleration, which is 739 meters per second squared. Times our time, which is 3.00 seconds. And so we get this change in linear velocity is equal to, and again, I'm maintaining 3 significant figures. If you were at 1 at this point, you need to maintain it as 1. And we get this as 2,220. This seconds will cancel with one of these, meters per second. That's how much the velocity changes during those 3 seconds. Whoa. Gosh. That's the second mistake I've made in 20 minutes. I apologize. You deserve better. 2,220 meters per second, so it's changed that much. If you rounded to one significant figure at this point, you should have 2,000. Because this would have been 800. 800 times 3 would be 2,400. You would round down to 2,000. Y'all have that? 2,000? And then, so that's the change in. That doesn't tell us what the ending velocity was. But if you know where you started, and you know you added 2,200 meters per second, how do you get what you end with? Yeah, add them together. So we started at 19.6 meters per second. This is the start. We add the 2,220 meters per second, and we get our ending velocity, our velocity after 3 seconds. Two thousand 2,240 meters per second. That's pretty crazy, right? Started at about 20 meters per second, which is about 40 miles an hour. Ends at 2,200 meters per second, which is about 4,500 miles an hour. Now this is assuming, of course, that there's no air resistance to compete that acceleration. But in that event, like if you were to do this in space, this is what it would be like. Okay, does this make sense? So this is the one I really wanted to do together. Yeah, Josh.
So why is it changing if there's nothing there but air?
Well, because there is something there. There's that force exerting that object away from the center of the circle. Right? So there's that force forcing that object away from the center of the circle. And so even once it's released, that acceleration is still present until you actually act on it with some kind of an outside force. Now, in reality, it wouldn't keep accelerating like that because you'd have other forces exerting, but it would accelerate some. That okay? All right. Okay, so that's homework number 5, and it's nice because we're actually going to attach what we were talking about the last couple of weeks of this angular motion into what we're talking about this week, kinetic energy. And our first question is this: why does the velocity of an object matter? Why do we care? So first, something we just saw in the previous problem. Did you get to write it down, Malachi? Okay. Is that when an object's velocity changes, it accelerates, right? We just saw that in our previous problem. If its velocity changes, it accelerates. And why does that matter? Well, that way we know that it requires some kind of a force to make that happen. It requires some kind of a force to make that happen. So that's one reason we care. If an object's velocity changes, we know that there's a force acting on it. That's one reason why we care about the velocity. Another reason we care about the velocity is because of Newton's first law. And it tells us even if an object isn't changing its velocity, that it resists a change in its velocity. Right? You all explained Newton's first law in your exam, that an object in motion remains in motion, or an object at rest remains at rest unless acted on by another force. So there's some resistance to a change in velocity. So a third reason why we care, these first two reasons we've talked about before, we haven't explicitly stated this is why we care about it, but we've talked about this before, right? We've talked about that an object doesn't change its velocity unless there's a force. What that means is an object's basically going to resist a change in its velocity. Here's a third reason, which we haven't talked about yet. Any object with velocity has energy. Any object with velocity, so any object that is moving, contains a certain amount of energy. And you might be thinking, well, why do we care about that? Well, one, you signed up for the physics class, right? So you care at least a little bit. But this energy, we call it kinetic energy, the energy of motion, the energy associated with something moving, and we can use this energy to do work. And we'll come back to that idea of doing work and when we talk about like what is energy. But I just want to introduce kinetic energy, energy of motion, energy associated with something moving. And we calculate this a very specific way. We calculate kinetic energy using this formula. 1/2 mv squared. 1/2 mv squared. M is the mass. They're our normal players. We've dealt with m of mass multiple times before. M is mass, v is velocity. And so what this formula shows us is because velocity is squared and mass is not, changing the velocity is going to have a lot larger of an impact on the kinetic energy than changing the mass would. Does that make sense? Because velocity is squared. So let's just think about this real quick, abstractly. I'll wait for you to write down what you're writing down, and then we'll think about it. We'll talk about it. Okay, true or false? A tiny rock, let's call it a pebble, moving at a very small speed has kinetic energy. True or false? Very small rock, let's call it a pebble, moving at a very slow speed has kinetic energy. True or false? True, right? Anything moving has kinetic energy, right? Any object with velocity, no matter how slow that velocity is, has some kinetic energy. May not have a great deal of kinetic energy, but it still has some. Okay? Now let's assume the speed stayed the same. Okay? Speed stayed the same. Wow, that was hard to say for some reason. Speed stayed the same, but this pebble picked up some other material on it. I don't know, maybe some algae grew on it, right? Moving slow enough, some algae sticks to it. And so the mass, let's just say the mass of this pebble doubles. So it's still a pretty small pebble, but now its mass is twice as much what it was before. How much would its kinetic energy increase? What's that? It would increase a little bit, but by what factor? So if this doubled, okay, let's just assume for simplicity, these are both 1. Okay, the mass is 1 gram, the velocity is 1 meter per second. Okay, 1 gram, 1 meter per second. All right? So here's 1 gram times 1 meter per second. What's 1 squared? 1. What's 1 times 1? 1. What's 1 times 1/2? 1/2, right? Well, now let's say the mass doubled. Now its mass is 2 grams instead of 1 gram. What's 1 squared? 1. What's 1 times 2? 2. What's 2 times 1/2? 1. How does 1 compare to 1/2 that it had before? It's twice as much. So if you double the mass, you're going to double the kinetic energy. Okay? All right. Now, the pebble did not gain that algae. Okay? Pebble's just the pebble. But instead of moving at 1 meter per second, it sped up to 2 meters per second. What caused the speed up? What's that? I mean, it could be anything, but just generally, what is it? What is the only thing that can cause an object to accelerate, to change its velocity? A force. Any force, right? Newton's first law. All right, so it still has a mass of 1 gram. Okay? But now its velocity is 2 meters per second. What's 2 squared? 4. What's 4 times 1? What's 4 times 1/2? 2. Remember, it started as 1/2, and now it's 2. What's the difference between 2 and 1/2? 4 times as great. So doubling the velocity quadrupled the kinetic energy. Doubling the mass doubled the kinetic energy. You see that? So because this is squared, a change of velocity is going to have a much larger impact on the change in kinetic energy than changing the mass would. Okay, keep that in mind. So when you're going through these problems and you find like a really large object versus a really small object, keep in mind that velocity is more important for determining kinetic energy than the masses. So you can have a really small object with a huge amount of kinetic energy if its velocity is really high. Make sense? Okay. All right, the reason I said that and we went through this little game is because the first practice problem we're going to do together is basically, let's reference back to this 5-gram rock, which 5 grams is a pretty small mass. Let's see, 5 grams would be 1/200th of a kilogram. I used a really small rock. I was going to give it to you in pounds, but it's small. So how much kinetic energy is in the 5-gram rock from the last homework problem? And this is assuming that we'll take that last, the ending velocity. Okay, so that ending velocity. How much kinetic energy is in the 5-gram rock from the previous problem? All right. So we have 5.00 grams, right? We know the mass of this rock. And we know the velocity of this rock because we went and we solved it. Kinetic energy, by the way, can be any velocity. So if you want to use linear velocity, we'll use linear velocity. If you want to use angular velocity, you can do that as you're calculating kinetic energy. So linear velocity, at the very end, we were at 2,240 meters per second. Let me get this out of your way, Malachi. Okay, 2,240 meters per second, right? We have a tool that says kinetic energy is equal to 1/2 times the mass times the velocity squared. And again, we can use any velocity here. You can use linear velocity, you can use angular velocity. What do we want? And I made this disappear so that Malachi could see what was on the board, but we want kinetic energy. And as I get this right further over, I need to remember to do that. So we want kinetic energy, which is nice. That's exactly how our tool is set up, is to solve for kinetic energy. So our kinetic energy is equal to 1/2 times our mass, which is 5.00 grams, times our velocity, which is 2,240 meters per second, squared. Right? So this squared is going to make the meters squared and the seconds squared. And we're going to have kinetic energy is equal to 2,240 times 2,240 times 5 grams times 1/2. Okay, and we should maintain it. This is how many significant figures? 3. This is 3, so we should present our answer in 3 significant figures. And we have 12,500,000 grams meters squared per second squared. True or false, this is a millinewton. I see a no from Stephen, because millinewton didn't have meters squared, did it? Millinewton was grams meters per second squared. Now we got some cool units going on here. We'll introduce what do we do with these units in a little bit. But here's our solution for the amount of kinetic energy in this small rock. 12,500,000 grams meters squared per second squared. Did you have a question, Colby? Okay. Can I bring this down, Malachi? Somebody remind me the next time I come over there to do a problem to start further over. Okay. How much kinetic energy is in a 5-kilogram boulder traveling at 20 meters per second? So we have the mass is equal to 5.00 kilograms. We have that our velocity, our linear velocity, is equal to 20 meters per second. We don't know for certain that this is linear velocity, but it'd be kind of a weird setup to get a boulder kind of rotating around, you know, in a circular motion. So tools, we still have the same tool, kinetic energy is equal to what? 1/2 times mass times velocity squared. Right? Okay, cool. What do we want? We want kinetic energy, which is wonderful. Our tool's already set up to help us to solve for that. So this is equal to 1/2 times our mass, which is 5.00 kilograms, times our velocity, which is 20 meters per second, squared. Okay, so squared's going to come down and make these both squared. Don't forget that as you multiply these through. So 20 times 20 times 5.00 times 1/2. And 20 has how many significant figures? Just one. So we need to present our answer in one significant figure. Kinetic energy is equal to 1,000 kilograms meters squared per second squared. True or false? This is a Newton. False. Newton doesn't have meters squared, right? Newton is kilograms meters per second squared. What if we did this though? What if we did this? Separate that meter out. Little algebraic trick, pulling, you call it factoring something out. Okay? Would this be the same thing as this? It'd be the same thing, right? It's still, this is meters times meters. This is meters times meters. We just pulled it out. Now, this would be, this is a Newton, right? So now we have this is 1,000 newtons times meters. Right? What about if we do the same thing over here? That's calming. This is the same thing, right? If we, instead of we say meters squared, we pull one of them out. We factor that meter out. Now what is this? It's a millinewton. 12,500,000 millinewton times meter. How many millimeters are in a meter? 1,000. How many milligrams are in a gram? 1,000. How many milliliters are in a liter? 1,000. It's a nice little milli means 1/1000th of something. Which means if we wanted to change this to newtons, we can do that. Because 1 newton equals 1,000 millinewtons. And I saved a lot of our discussion for units and our the SI units metric system for when we use it in context. I didn't want to have a whole day where we just dealt with units because it's boring. And I want you to be bored. I want you to enjoy yourself. And I know what you're thinking. You're like, if you want us to enjoy ourselves, you ought to do a better job of entertaining us. Try. Okay? So if 1 newton is 1,000 millinewtons, if we wanted to convert this into newton meters, what would we divide it by? 1,000. So if you wanted to go from millinewtons to newtons, we would divide this number by 1,000. So we'll drop the last 3 zeros. Okay, right? $12,500 Newton meters. What was the kinetic energy over there? 1,000 Newton meters. So we had a rock. The rock over there is 1,000 times heavier than this rock. Right? 1 kilogram is 1,000 grams. So that rock is 1,000 times heavier than this rock. This rock has more kinetic energy. You see that? Not just a little bit more, a lot more kinetic energy. 12 times as much. Why? Velocity is way higher than the other one. Okay? More than 10 times as much. And that's why I told you, velocity makes a larger impact on the kinetic energy than mass does. Okay? So there you have a rock 1,000 times the size of this rock, but this rock is traveling at basically, what would that be, 100 times what this one is, but 100 times squared becomes 10,000 times. So, all right, velocity makes a bigger impact on kinetic energy than mass. And I illustrated it with our first 2 examples. Are there any questions here? So I know this was a little bit weird. I just wanted to do this for comparative sake. If you're not super comfortable converting from millinewtons into newtons, that's okay, because I will walk you through that in terms of if you ever have to do it on a homework problem. I'll help you to do it. I just wanted to do it for comparison's sake, so that we can go and show you exactly. And I could have just said that this was 5,000 grams, and then that would have solved that problem, but I didn't. Okay, everyone all right with that? So what makes a bigger impact on kinetic energy, mass or velocity? Velocity, especially when you change them. All right, so our next framing question. What is energy and why should we care? What is energy and why should we care? What is energy and why should we care? So I mentioned this in our previous slide, but I'll bring it back up. Energy is the capacity to do work. So any object moving has what type of energy? Kinetic energy, right? Any object that's moving has kinetic energy. And energy, it's the capacity to do work. Well, that doesn't tell us a whole lot unless you know what work is. Right? So here's what work is. Work is some force executed over a distance. And I gave you an example here, pushing an electric car to your driveway to charge. So for 3 years, I had an electric car. Any of you ever been in an electric car? So you have, associated with electric cars, you have what's called charge anxiety. Because it's not like a fuel-powered car. Even a hybrid car takes gasoline, right? So if it gets really low, there are a ton of gasoline stations for you to just pull in and fill up. An electric car, it's a little bit more complicated. There are some charging stations spread around, but not like there are gas stations. And it's not like you go into a gas station, it takes you, 5, maybe 10 minutes at most if you have to run in to actually, pay for the gasoline. 5 or 10 minutes at most. You got to charge an electric car, it takes you hours to charge your electric car. So people get a lot of charge anxiety. My wife couldn't handle it. She's like, I can't drive that electric car. But it was nice for me. It was enough to make it here and back on a single charge. And I never ran out of charge. My wife was telling me, like, you're going to run out of charge, but I had it timed perfectly so that I could make it here and back on a single charge. It was perfect. Like, I'd come home and I'd have, like, the thing would be flashing saying you have no charge left. And it's like, that's fine, I'm home. I don't need any charge left. I plug it in. One day, I went and ran an errand while I was here. So I didn't just come from my home to here and then back home. I actually went and ran an errand. And I thought, it's okay, I should have enough. I did not have enough. And I actually ran out of electricity about 2 miles from my house. And this was going to be me pushing an electric car from that place 2 miles into my driveway so I could charge it. But instead, I had it towed. I was not going to push it, so I had it towed. And my kids were all upstairs watching, laughing as the tow truck dropped my electric car into the driveway. Yeah. Another thing about energy that we should care, energy can't be created, it can't be destroyed. So the amount of energy available in the universe, it remains constant. There's always the same amount of energy. However, it can change form and move from one object to another. So the rock that we've been using over and over and over again in our example to another object, like Goliath's head. Okay, so if you've got an object with a large amount of kinetic energy, like that rock has, 12,500 Newton meters, that energy can move from kinetic energy in the rock to kinetic energy in Goliath, right? And actually knock him maybe even off of his feet. You could go through and figure out how much energy that is. Yeah.
So where would it go after it went to his head?
Well, it probably wouldn't have gone clean through. It probably would have just went and kind of made it just a mess of his skull and his brain.
But it would have to change to something else, right?
Yeah, so eventually it would change to heat. A lot of that energy would be lost as heat. Some of the energy would be lost as sound waves, that type of energy, and then some of the energy would have continued as kinetic energy and then been converted into some other form. But yeah, most of it would have been lost as heat and sound. So energy, we measure energy in joules, and a joule is equivalent to a Newton meter. You see this over here? We've got newtons times meter, right? So we have this was 1,000 Newton meters, and what is a joule equal to? A Newton meter, right? You see that? Do you see it? Okay, so which means we could also write this answer as 1,000 joules. It means we could also write this answer over here as 12,500 joules. And joules are going to be a really important unit because we're going to deal with this a lot. Joules are the unit for work. Joules are the unit for energy. Joules come up a lot. It's not the only way to measure energy, but it is the most common way to measure energy in most places in the world, not where we live. Do any of you know how we measure energy here in the U.S.? You see it on every food package. Most fast food restaurants that you go to, most restaurants that you go to will have it in their menu. We're supposed to eat about 2,000 a day calories. So we can also measure energy in calories. And 1 calorie, there's your conversion ratio. 1 calorie is equal to 4.184 joules. But the food calories are actually kilocalories. 1,000 calories in 1 food calorie, which is unfortunate that they didn't actually change the term. So when I do that, I'll represent it in kilocalories, like kilograms, kilometers, kilometers, however you want to say it, kilonewtons, kilojoules, kilowatts. All right, is this okay? So why do we care about energy? We care. Oh, go ahead. Yeah, it's the capacity to actually to do work, to take objects and to move them, to accomplish something. We also care about energy because it can't be created. It can't be destroyed. It could just be converted from one form of energy to another. All right, got a couple more example problems to do, and then we'll be done. Okay, so how many joules of energy are in a breakfast bar that contains 125 kilocalories of energy? And so if you were to look on a wrapper, it would just say 125 calories, but those are kilocalories. They just get around writing kilocalories by putting a capital C on it instead of a lowercase c. So how many joules of energy are in a breakfast bar that contains 125 kilocalories of energy? So we know the amount of energy, right? What does the energy equal to? It equals 125 kilocalories. Right? So this bar, whatever this breakfast bar is, has 125 calories in it. It's 125 kilocalories of energy. A tool, we know that 1 calorie is equal to 4.184 joules. Right? We know also that 1 kilocalorie is equal to 1,000 calories. That's what this root kilo means. 1 kilometer is 1,000 meters. 1 kilogram is 1,000 grams, so on and so forth. What do we want? Joules. We want joules. So first we're going to need to convert from kilocalories into calories. So 125 kilocalories times 1,000 is equal to 125,000 calories. You okay with that so far? 125 kilocalories. We multiply it by 1,000 and we get 125,000 calories. And then if you wanted to put in your units here, this is calories per kilocalorie. And then that way kilocalorie canceled here, kilocalorie canceled there, and we'd be left just with calories. Is that okay? Okay. And then we have 125,000 calories times 4.184 joules per calorie is equal to, calories will cancel, 125,000 times 4.184 joules per calorie, and we have 523,000 joules. 523,000 joules. Do you remember our rock? It was 1,000 joules, right? 523,000 joules. It's a lot of energy. Where does it all go? The answer is in us, most of it goes towards heat production to keep our bodies from freezing to death. But some of it goes into growing and developing and, just rocking life, running up the side of a mountain, whatever you want to do. Gives you put some of these things in context, right? Takes an enormous amount of energy to be human. All right. How fast is a 650.5 kilogram car traveling if it has 7.85 kilojoules of energy? Is the car moving? Yeah. So what type of energy does it have? What's the energy of moving objects? Kinetic energy. So we know that the kinetic energy is equal to 7.85 kilojoules of energy, right? Problem gives us that. We also know the mass of the car is equal to 650.5 kilograms. And then some of the tools. We know that kinetic energy is equal to 1/2 mass times velocity squared. We know that 1 kilojoule is equal to 1,000 joules. And then what do we want? What is this problem asking for? Velocity, right? How fast is the car traveling? So how do we get this away from the velocity? I don't want it there. We could divide each side by 1/2 times the mass. These will cancel to give us 1/2 times the mass. And now its velocity squared is equal to this. How do we get rid of that squared? What's the opposite of squaring something? So 5 times 5 is 25. What would we do to 25 to get us back to 5? Take the square root, right? May not be super comfortable, but does it make a little bit of sense? So if we want to get rid of the square, we've got to take the square root of both sides. So what we get is we get that velocity is equal to the square root of kinetic energy divided by 1/2 times the mass. This one was a little bit more complex algebraically than what we've been dealing with for the past couple of weeks. So I'll make sure that I'll put onto our digital course space, which your grades are on there as well. I'll send out an email with the slides and the link to the video with the link to our digital course space, and I'll give you some more problems like this to solve, more practice problems like this. And then if you struggle on the homework to do one like this, let me know, and I'd be happy to help. The one on the homework actually asks you to solve for mass instead of velocity, so you don't actually have to worry about taking the square root. So velocity is equal to the square root of our kinetic energy, which is, first let's get that into kilojoules, or into joules. So 7.85 kilojoules times 1,000 joules per kilojoule. And so we get velocity is equal to 7,850 joules divided by 1/2 times our mass, which is 650 kilograms. Okay? All right. So we'll figure out the units in a second, but let's do this. So 7,850 divided by 1/2 divided by 650, the square root of that number, and we get that our velocity is equal to, this is 3 significant figures. This is, it's 650.5. Why did I leave that off? It's not going to make a huge issue in our calculations. So we'll limit our answer to 3 significant figures, and we'll get 4.91. And now we need to figure out what to do with our units. This is kind of weird, right? Square root, it's awkward. But when you actually do the calculations of the number, you get 4.91. What is a joule equal to unit-wise? Do you agree that a joule equals that? A Newton meter? Do you agree that a Newton is kilograms, meters per second squared? Kind of working backwards a little bit. Kilograms cancel, right? Kilograms divided by kilograms, these are going to cancel. Meters, meter times meter, if you take the square root of meter times meter, you're left with just meter, right? You take the square root of second squared, what do you get? Just seconds. So our units would be meters per second. Why is that good? What did we want to find? A velocity. And what are our units for velocity often? Meters per second. So this car is traveling at 4.91 meters per second, which is about 10 miles an hour. So a car traveling at about 10 miles per hour has a kinetic energy greater than that boulder in our experiment, in our problem, traveling at 20 meters per second, and almost as much energy as the rock from our example, which was 12,000 instead of 7,000. But way less energy than we got from eating that breakfast bar. Okay? And you're like, wow, a car traveling at 10 miles an hour, that's a lot of energy. It's nowhere near the amount of energy you get from eating a breakfast bar. It's expensive, right? It's expensive being human, energetically, of course. Right? Make sense? Cool. You have your work. Go ahead and hold on to those folders, and when it comes time to turn work in, you can just turn it right back in those folders. If as you're working through your homework, on these slides, it'll be homework 6 is attached to it, and as is quiz 2 is attached to the back of these slides. And so you'll see those. I'll send you the link with the video and these slides, and I'll also put some